This is a lesson on solving initial value problems in vector calculus. We're going to start by looking at a one variable problem. And this is often the way we learn vector calculus, is by checking out how things worked in the one variable case and then using that as a way to motivate how we look at the processes in the multivariable case. So let's start by looking at this first order initial value problem. So an initial value problem would consist of a differential equation, in this case y prime equals e to the 2x plus 1, and an initial condition, here it's y of 0 equals 3. Another way to write these initial conditions, so this one here would be equivalent to saying x equals 0 when y equals 3. And to solve an initial value problem, what we're trying to do is find a function y that satisfies this equation, this differential equation, and also satisfies the initial condition. So we would integrate this differential equation to uncover the derivative up to a constant. So it is 1/2 e to the 2x plus x plus a constant. And it's a good idea to check these things, as differentiation is much easier than integration and could save you some time in the long run. So a quick check here, the derivative of e to the 2x using the chain rule would be e to the 2x times 2, canceling the 1/2 and bringing us to the e to the 2x we want. And of course the derivative of x is 1 and the derivative of c is 0. Since we haven't specified the constant c, this is called the general solution. But we're after finding a specific solution that also satisfies this initial condition. So what we'll do is use that initial condition, x equals 0, y equals 3, to solve for the constant c. So on the right, when we plug in x equals 0, we end up with 1/2 plus c. And on the left, we have y equals 3. A common mistake is to assume that the constant c is the value of your initial condition. And that could happen. And we'll see examples, and it often happens in applications. So sometimes folks rush to conclude that c is the value 3. But in this case, we can see that it's not, because by plugging in x equals 0 and then solving for c, we see that c is 5/2. This tells us the specific solution is 1/2 e to the 2x plus x plus c, which in this case is 5/2. And that's the solution we're looking for. If you understood that last example, the great news is we can apply that process to a vector calculus initial value problem, and the only difference is that we need to keep track of more components. So let's take a look at a vector calculus initial value problem, and let's start with one in 2D, 2 dimensions. So we'll be given a derivative of a vector valued function. In this case, I'll use r prime of t equals, and let's use that same function e to the 2t since we're familiar with it, and also sine of t for our y component. Now the initial condition here would be of the form, what is r at some initial time, which by the way does not have to be 0. We could use other values. 0 is a convenience here. And the initial condition would be a vector quantity. We'd need an initial condition for the first x part of the problem. And in this case, let's just put some numbers in here, like 2 and say -1. All right, so to solve this initial value problem means that we're looking for a solution R of t that has the property that when we take its derivative, we get this vector function, and also has the property that when we plug in t equals 0, that the value r should be 2 minus 1. So another way to write this here, this would be equivalent to saying t equals 0 and r at that value equals 2 negative 1. Or we could say when here. Okay, as before, we'll just do an integral here to uncover the derivative. So integrating both sides would give us r of t equals the integral of e to the 2t, which is 1/2 e to the 2t. And we're going to have a constant of integration, which we could put on the side over here as a vector, or we could individually put our constants in, which is just as efficient or more efficient in a problem like this. So we're going to add in a constant of integration, and I'm going to use a subscript 1 to distinguish it between the constant of integration and our next component. Now, integrating sine gives us minus cosine, and then plus another arbitrary constant we'll call C2. Since we haven't specified these constants, this would be called the general solution. To find a particular solution, and in fact the solution that we want, we would plug in our initial condition. So a lot of times that's abbreviated just IC. So using the initial condition right here, we would on the right be plugging in t equals 0. And here's the right side. I'm plugging in t equals 0, and we would end up with 1/2 e to the 0, which is 1, plus c1. And negative cosine of 0 is negative 1 plus c2. And we are given that that should equal 2 negative 1. So on the left, we put 2 negative 1. So notice that this is really the same procedure as in the one variable case. We're just doing twice as much. And solving here for these constants, the only way two vectors can be equal is if each of their components are equal. So we get two separate equations. 2 equals 1/2 plus c1, and negative 1 equals negative 1 plus c2. Those are relatively easy to solve for. So in this case, we would have c1 equals 3/2 and c2 equals 0. But finally, we get the specific solution we were after. The solution to our problem is the general solution that we'd found by integration, where we're plugging in the constants c1 and c2 that we found using the initial conditions. So in this case, we have 1/2 e to the 2t plus c1, which we found to be 3/2. And then our c2 we found to be 0, so we would end up with minus cosine t. It's easy to check by differentiation. Differentiating, we have e to the 2t plus 0 when we take the derivative. So that matches with our original r prime, which was e to the 2t sine t. And plugging in the value of t equals 0 gives us 1/2 plus 3/2 is 2, which is what we wanted for our initial condition. And similar for our y component, taking the derivative gives us sine of t, which we wanted. And if we plug in t equals 0, we get negative 1, which we wanted. So this solution checks out. That's the end of this lesson. We'll have a part 2 coming up where we look at some applications in 2 and 3 dimensions. Thanks for listening.